have starting the first talk today by Michelangelo Mangano. We have other talks as I show you in this slide. And I would like to call Wagner Carvalho, is a professor of University of the State of Rio de Janeiro, to be the moderator and call the speaker. Thank you very much. Have a good day.
Thank you, Santoro. Good morning to everybody. Before starting, I would like to remind you that you can, if you are attendee, you can post your questions using the button in the bottom of the page, the Q&A button, okay? And if you are a panelist, you cannot do it, so you just raise your hand and use the microphone, okay. I also would ask, kindly ask the speakers to try to keep to the time, okay? I think everybody has half hour to give the talk. And then I will introduce our first speaker. Our first speaker is Professor Michelangelo Mangano. He'll talk about the physics of future circular colliders. Professor Mangano is a graduate of Scuola Normale Superiore di Pisa in Italy. He held research positions at the University of Princeton, United States, in the National Institute of Nuclear Physics, Italy, and the FabLab National Accelerator Laboratory in the United States, and where he contributed to the observation of the top quark in 1994. And since 1995, he's a senior theoretical physicist at CERN, where he leads the LHC Physics Center and has coordinated since 2013 the physics studies for a future generation of circular colliders. So, Professor Mangano, please, you have the microphone.
Thank you, Wagner. Wagner, can you remind me how much time I have, in fact, because I'm confused a bit by the agenda. I thought I had half an hour, but then there is much more there.
It's 30 minutes, okay? If you want, I can
minutes. Okay.
give a warning 5 minutes before if you... Oops. I don't see Professor Mangano anymore. I think something happened.
What happened? Something wrong happened. I got kicked out, so I will connect again.
Okay.
All right. Okay, can you confirm that everything is okay, that you can see it?
Yes, perfect.
Okay, very good. So yeah, if you can give me a warning, say 5 minutes before the end, so I will be able to wrap it up on time. So good morning, everyone. Good afternoon for those of us here. I will put the discussion of these future circular colliders, of course, in the context of the big open questions we have in high energy physics. We all know what they are, finding the origin of many phenomena beyond the standard model, like dark matter, neutrino masses, the asymmetry between matter and antimatter. And aside from puzzles, from open questions that arise from data, there are, of course, theoretical puzzles that theorists at least are confronting, like the hierarchy problem, naturalness, the origin of inflation, the flavor problem. So there is no, these are all interesting questions, but we have no guarantee as to where answers to these questions will come from. What are the experiments that will absolutely and with certainty provide them? And that, of course, means that we need a very diverse program, experimental program in high energy physics to make sure that we have the appropriate experiment to cover, say, for instance, to discover dark matter independently of what dark matter actually is. As you know, dark matter can be anything between a fuzzy boson with a mass of 10 to the minus 20 electron volts all the way up to something like primordial black holes, going through pretty much every point in the mass spectrum. Of course, the range between the GeV and the TeV is favored by the so-called WIMP models, but dark matter, of course, could be neutrinos, could be axions, could be combinations of all of these, and certainly could be something we haven't thought of as yet. So there is not a clear, you cannot build an experiment that will absolutely deliver the discovery of dark matter. There is one question among the fundamental questions we have, however, for which only colliders can provide, if at all, an answer. And so future collider efforts have to focus on the thorough exploration of this question. And the question is, where does the Higgs potential come from? It seems like a trivial question, but the Higgs potential is really built in by hand in the Standard Model. It's an entirely phenomenological description of an important phenomenon, a key phenomenon, which is crucial to explain the presence of mass for gauge bosons. But precisely where that potential comes from is not known. The search for the origin of the Higgs and the electroweak symmetry breaking, therefore, is justified independently of whether we have a theoretical prejudice on how important, say, the hierarchy problem is. It's not just a matter of, how far is the electroweak scale from the Planck scale, which is puzzling. It's really finding the origin of the Higgs, finding the origin of electroweak symmetry breaking, which is a crucial question. Now, since the electroweak symmetry breaking is physics taking place at the TeV scale, it's reasonable to expect that the dynamics that causes it is also there. And that is what justified the hope that new physics would be seen by the LHC. Since it's not being seen, of course, many new ideas are emerging, which postpone to higher energies or provide completely alternative scenarios to understand the origin of the weak scale. On the other hand, the detailed experimental investigation of the Higgs properties remains absolutely crucial. It's a sine qua non condition if we want to make progress, independently of what is our bias. Whether we do believe that there is no physics close to the electroweak scale, or whether the origin of electroweak physics and symmetry breaking is at much higher scale or in some other framework, we cannot go anywhere unless we have fully clarified the full set of Higgs interaction and Higgs properties. And this is what led the European strategy last year to conclude that what we need is a Higgs factory as the next machine. That should be the highest priority next collider, and it would be an electron-positron Higgs factory because that is the most easily obtainable and also the most accurate as a starting point for the exploration of the Higgs. So that really sets the frame for the design and the concept of future facilities. They must provide a precise measurement of the Higgs properties. That has to be a guaranteed deliverable of any future collider. Now, whether the measurements will challenge or will confirm the Standard Model properties, these measurements will be absolutely key if we want to explore physics beyond the Standard Model. Of course, if the measurements of the Higgs properties show deviations from the Standard Model, then obviously we know that there is a hint to beyond the Standard Model physics. The correlations among the deviations in Higgs properties, say in different decay modes or production modes, of course, will guide the interpretation of the origin of these deviations. But even if the measurements of Higgs properties will agree with the standard model, that will be very important information, especially if these measurements are very accurate. And the reason is that the day we will find BSM physics, perhaps directly through a resonance or maybe exploring flavor properties, or you name it, the first thing that we will need to do is to understand what is the origin of this new BSM physics, what's the microscopic origin. And then we will have to confront any model that we were to come up with the fact that the Higgs properties agrees with the standard model. It would be a very, very powerful constraint on any possible interpretation of new physics, which is a bit like what has happened in the past 20 years with the measurements from LISHEP. LISHEP proved the consistency of standard model predictions with data to high approximation, to high precision. And every time there is some anomaly detected in the data and people start building models, the first thing they do, they check whether their models make any sense by going back to the lab data. And very often the models are inconsistent with the constraints coming from lab, and therefore you have to throw them away. And very often it turns out that the lab data are so constraining that presumably the anomaly that you're looking at must be fake, because there is no model you can write that is compatible with the strong constraints from lab. So the same will have to be true for the Higgs. The same, we have to set up a framework in which we can use Higgs data in such a powerful way, independently whether they agree or they don't with the standard model. Of course, in the Higgs sector, there are many other important issues. Of course, we've seen a scalar now, presumably a fundamental one. The question is whether there are more. Are there charged Higgses? Are there Higgses with different CP properties or even electroweak couplings, whether the Higgs gives mass to all of the families, whether there is a flavor violation in Higgs couplings. And of course, all of these are questions that touch on potential beyond the standard model properties of the Higgs, connections of the Higgs to dark matter, to inflation, the context of understanding the electroweak phase transition during the Big Bang. All of these are questions that use the Higgs as a tool to probe and explore physics beyond the standard model. So the Higgs discovery does not close the book, it just opens a whole new chapter of exploration. It gives us a new tool on which we can probe new physics. And again, the only way in which we can study and determine the Higgs properties is by producing Higgses. So that does require a future generation of colliders. Of course, when we talk about future colliders, we also want to know how come the LHC, which by itself was supposed to discover, was expected to see new physics beyond the Higgs, hasn't seen anything? Why don't we see the new physics we expected to see at the TeV scale? Of course, it could be that the mass scale is beyond the LHC reach, or it could be that the mass scale is within the LHC reach, but the final states are elusive to the direct search. There could be large backgrounds, they may not be triggerable, and you name it. So if we want to make progress and we want to design the future facility, the future huge accelerator, we better make sure that we cover both of these scenarios. So precision and sensitivity, of course, which can be achieved by improving the accuracy of the measurements, say with indeed the future plus minus colliders, help us address the case where the mass scale is, for instance, within the LHC reach, so relatively light, but the final states are too hard to see in a hadronic context. But if indeed the mass scale of new physics is well beyond the LHC reach, the only way to get direct access to it, to create these new particles, is to go to higher energy. So that's why also a follow-up of the European strategy recommendations is to make sure that not only you want to have as soon as possible any plus or minus Higgs factory, but you also should also aim at having the next generation Hadron Collider. That's the only way we can reach directly the scale of multi-tens of TeV. So these challenges, namely being able to address both precision and therefore the indirect reach of high scales through precision measurements with the plus and minus collisions, and the direct reach, which means directly creating new particles. These challenges can be met by this facility, which was called the Future Circular Collider, which is just an extension of the LISHEP and LHC story within a 100-kilometer tunnel. I will not go into any of the details because I'm sure that by now it's already been 7 or 8 years that CERN has been discussing this, and I'm quite confident that each of you has seen this before. So what is it that the Future Circular Collider can offer? There is a set of guaranteed deliverables, which of course starts from the study of the Higgs and the top quark properties and the exploration of electroweak symmetry breaking with precision and sensitivity that cannot be matched by any other proposed facility. There is in parallel this huge exploration potential. Part of it comes from, again, the ability to probe high, to explore through precision measurements, but also the enhanced mass reach for direct observation of new states that comes from having access to 100 TeV. And as I will show you later, this 100 TeV somehow energy scale is very well suited to match the mass scale that could emerge from indirect precision measurements. Finally, while there is of course no guaranteed discovery that can be promised, no facility can promise, as I said before, to guarantee the discovery of, say, dark matter, there could be a guarantee to provide conclusive yes or no answers to very important questions. For example, there is a question like, is dark matter a thermal WIMP, a weakly interacting massive particle? A thermal WIMP there are upper limits on its mass that comes from general theoretical arguments, and they set this mass at about 1 to 3, 4 TeV, depending on the precise value of the weak couplings, whether it's a weak doublet or a triplet or other representation of SU2 cross U1. But there is an upper mass limit, and this upper mass limit, which, as I said, it's in the range of 1 or few TeV, is well beyond what the LHC can do. So the question is, would the FCC be sufficiently powerful to discover a thermal WIMP throughout the full possible spectrum, theoretical spectrum of its mass? That would be a very interesting conclusion. A big open question is, what was the nature of the electroweak phase transition during the Big Bang? In the Standard Model, it's a smooth crossover. In principle, it could have been a strong first-order phase transition if there were no physics. And if it had been a strong first-order phase transition, that would have given rise to, for example, stochastic gravitational waves. It could have been the seed for the creation of the baryon, anti-baryon asymmetry. So that is an important question, and we would hope that the next facility is able to answer in a conclusive way a question like this. So this is somehow, this picture summarizes the power of this facility, because it gives you an idea of event rates that we're dealing with. A canonical Higgs factory, like even ILC or CLIC, will deliver of the order of 1 million Higgses, and so will the FCC EE. But in addition to, so from the point of view of pure Higgs physics, there is a large similarity between what different machines can provide. But the one thing which is unique to the circular E plus E minus collider is the ability, for example, to create trillions of Z bosons and hundreds of millions of W bosons. And of course, these statistics that would come from runs at the dedicated energies, at the Z pole, at the WW threshold, and also it's possible to get above, slightly above the TT bar threshold. All of these runs would provide immense statistics, 10 to the 4, 10 to the 5 times bigger than what LISHEP could give, opening a completely new perspective on electroweak physics, as well as flavor physics, because every time a Z decays, it could go to taus, to Bs, to charm. And the samples of tau, Bs, and charm that you get out of the Z decays at the E plus E minus collider are beyond what any other low energy plus E minus machine can do, including LISHEP, including Bell 2. The Hadron Collider, now we're talking about tens of billions of Higgses being produced. Of course, it's much harder to use Higgses produced in hadron collisions, but the statistics is so large that one can get away from dirty and systematics dominated regions and operate with very clean samples of Higgs. Trillions of top quarks will be created, and as a result, also trillions of W bosons just from the decay of a top, let alone the inclusive Ws. In addition, it's possible to use electron and protons and collide them, adding somehow complementary samples of Higgses and single tops with different somehow sensitivity to the respective properties. So a few words about some of the, in concrete, the guaranteed deliverables. I will start from the Higgs properties. And just to give a sense of what the target should be in the precision, how precise should Higgs measurements be? I take this table from this paper prepared by our ILC colleagues a couple of years ago. This is a collection of models beyond the standard model, starting from supersymmetric models to 2 Higgs doublets, composite Higgses, etc. These are all models which, in their details, have not been as yet excluded, let alone discovered, by the LHC, but these are models that even the high luminosity LHC may not be able to see, because again, they're difficult to trigger on, or they have backgrounds, simply that they're not easily visible. So for each of these models, they calculated the impact on the couplings of the Higgs to different standard model particles, the V, the charm, the gluon, Ws, taus, etc. And they plot and they list in this table the deviations in percent from the standard model coupling. And you see that there are a couple of cases where we are at the 10% level, a few more cases where we are between 5 and 10%, that's the blue boxes. Everything else is well below the 5%. And that means that if we really want to achieve a 3 to 5 sigma evidence of deviation, something we can believe in, we have to achieve typically sub-percent precision. So the sub-percent or sub-percent precision must be the target of precision for the future generation of Higgs measurements. The unique power of the plus E minus, and that's why plus E minus is given a priority in the European strategy. And this is true of whether the plus E minus is circular or linear. The unique power is the model-independent absolute measurement of the coupling of the Higgs to the Z boson, the Higgs-Z-Z coupling. And that comes about from the associative production on a Z of a Higgs. One uses the recoil momentum, which is the momentum of the initial state minus the momentum of a fully reconstructed Z decay. For example, Z goes to mu plus mu minus. So the momentum of the recoil is perfectly known independently of the determination of the recoil kinematics. And we take the 4 momentum of the recoil, we take the square, and that if we have produced a resonance like the Higgs, will manifest itself with a peak, as is shown in the figure here. So we just look at this peak, which again does not rely on any measurement of the actual decay modes of the Higgs, and this just counts in absolute terms how many Higgses were produced, and therefore measures the coupling of the Higgs to the Z. So this is a measurement that only plus and minus can do. That measurement is then the starting point for the absolute determination of the Higgs to ZZ branching ratio and all of the other branching ratios that can be accessed. The unique power of PP2H is the extraordinary statistics, as I mentioned before. When we put together the statistics that we have in PP with the precision and the absolute measurement of the Higgs to ZZ star branching ratio and the Higgs to ZZ star coupling that came from the plus and minus collider, we can promote to sub% precision the measurement of decay modes, which are too rare for the plus and minus to measure with any precision. And in addition to that, we can bring to below the 5% the measurement of the Higgs trilinear self-coupling, something that no plus and minus machine can do, again, just because of statistics. Furthermore, a huge dynamic range with PTH, all the momentum of the Higgs up to several TeV is possible when we have 100 TeV in the initial state. So these are some statistics, 25 billions of Higgses produced in glue-glue, 2 billions in vector boson fusion, and hundreds of millions in associated production with the W, with the Z, or with the top. So the Higgs spectrum will extend all the way up to the multi-TeV region with statistics which are very, very large. Here you see the number of Higgses produced during the 30 inverse attoburn integrated luminosity of a 100 TeV collider. That's the number of Higgses produced with a transverse momentum larger than a given threshold. So if we take 1 TeV, 1000 GeV, you see there is more than several millions Higgses produced. And when the Higgs is boosted so much, all of the analysis becomes more clear. Many of the systematics are reduced, and even the fact that we're working in a very challenging pile-up context, that becomes less of an issue. So there are three kinematic regimes, the inclusive one, when one is, as at the LHC, one is fighting against pile-up backgrounds and triggers. There is a regime of a slightly boosted Higgs above 100 GeV, where many of the trigger background and pile-up issues are reduced, but where there is still an immense statistics. And finally, there is the region of PT above a TeV, when one is looking at new dynamics. Somehow the production properties are more interesting in this case than the decay properties. We want to see if we take a Higgs and we probe it with a 1 TeV probe, at very, very short distance, does it still behave as we expect? Does it still behave as a point-like particle, for example, or does it manifest some evidence of compositeness? So that's the advantage of being able to go to several TeV. So this is just one example of analysis that one could do with Higgses in the few hundred GeV domain, without going through the details. The conclusion of this study, in which the spectrum of the Higgs in the gamma-gamma final state is compared against, say, the gamma-gamma QCD background. This shows that signal to background, if you look at this plot in the upper right, the signal to background, which is about 1 to 30 for the inclusive Higgs, goes up to about 1 or more when the Higgs PT goes above a couple of 100 GeV. So if you take a 200 GeV diphoton pair with mass close to 125 GeV, it's more likely to be a Higgs than to be a background. So that clearly makes the analysis much more robust and simple. And at 100 TeV, so for PT of the Higgs above 100 TeV, we're talking about a 2 per mil statistical precision. So these very precise measurements of different rare decay modes, like Higgs to gamma-gamma, Higgs to 4 leptons, Higgs to Z gamma, Higgs to mu plus mu minus, one can take ratios of these, normalizing to Higgs to ZZ star, which is known absolute from E plus E minus, and that automatically returns.
5 minutes, please.
Thanks. That returns an absolute measurement of a branching ratio in those rare channels. So the bottom line, when we put everything together, is that between the FCC-EE and the FCC-HH, we managed to push to the percent level or below pretty much all couplings of the Higgs to the second and the third generation. There is also a 5% precision on the Higgs self-coupling. I have a slide here on the Higgs self-coupling that is I'm going to skip because of time. I mentioned the value of measuring Higgs is a very large Q square, and that's because if there is any deviation in the Higgs couplings, say parameterized by one of these dimension 6 effective field theory operators, the impact on observables at large scale Q will be proportional to Q divided by lambda, where lambda is the scale defining the new physics squared. And when Q becomes large, these effects get enhanced. So we have this complementary approach to deviations, standard model deviations in the Higgs properties. One is from the very precise measurements of, say, Higgs decays at low scale, and the other is from precise measurements at very high Q of a production dynamics. And these two complementary approaches could help, of course, disentangle the origin of possible deviations observed in the data. Here I have a table with the evolution of a precision in electroweak measurements. As I said before, statistics goes up by a factor of 10 to the 4, 10 to the 5 with respect to LEP. So we can anticipate improvements in the precision of electroweak observables in the range of 10 to 100, typically 100, and that could be limited a bit perhaps by theoretical or experimental systematics, but you know, at least a factor of 10 improvement throughout the board is guaranteed. Now, the discovery reached at high mass. Why do we need 100 TeV? Well, you see it from this plot. This plot shows the sensitivity to the scale lambda, which is shown here on the y-axis, of different operators beyond the standard model obtained doing electroweak or Higgs precision measurements. So through electroweak and Higgs precision measurements, depending on the operator here, we get to probe scales which are, as you see, in the range of 10, 20, 30 TeV, occasionally even higher, but typically we are at the level of 30 TeV. So with 100 TeV, if there is no physics at 30 TeV, the 100 TeV proton-proton collider is the minimum somehow that you want to have in order to directly access this physics. It's easy to project to 100 TeV what the discovery reach would be, starting from the experience of LHC, because 100 is 7 times 14, and you would imagine that at the high mass, at least, you're really driven by the overall center of mass energy. So you take all of these figures with limits on supersymmetry and Z primes and whatever, you multiply them by 5 or 6 or 7, and you get a sense of where we can go with 100 TeV. This can be done, of course, precisely with simulations. And you see, for instance, with Z primes or excited quarks into digits, the mass reach for 5 sigma discovery ranges between 10 and 40 TeV, which is precisely what matches the needs coming from precision measurements. Supersymmetry, squarks and gluinos up to 15 and 20 TeV, stops up to 10 TeV. For what concerns dark matter, here I have a slide illustrating the origin of these upper limits on the mass of WIMPs, which are theoretical limits, but they, as you see, we have a mass which is bounded from above at the level of UTV, and detailed analysis of various classes of WIMP models at this upper mass range confirm that indeed they can be discovered. So that there is a possibility of these no-lose theorems for the observation of WIMPs. I haven't covered many, of course, of the results that can be obtained from the FCC. This ranges from a very, very thorough set of multiple BSM scenarios, including also heavy neutrinos, discussing the issue of the original neutrino masses, long-lived particles, other versions of dark matter. There is flavor physics, especially from Z decays. I mentioned before these 10 to the 11 B's, taus, and charms being produced. And of course, there is a rich program of heavy ion physics in the same way that we have it at the LHC. So here are my final remarks. I stressed the relevance of addressing the origin of the Higgs phenomenon and of the electroweak potential. I showed how the interplay between the ± and the Hadron Collider is extremely fruitful. It's really unique compared to other possible projects relying on just, say, for instance, with a linear version of EE. What is unique is the possibility to match the indirect high mass scale sensitivity of a precision measurements to the direct search potential that we have at large mass. And that really what singles out this facility as the best possible somehow future option in terms of breadth, diversity, and ability to sort out new phenomena. And we have now 5 or 6 years for what is called the feasibility assessment to, on one side, iron out the various technical challenges in this project, and then, of course, also to try to find the proper political support for it. Thank you.
Thank you for your very nice talk. We have a question here. Actually, we have two. Okay, so Gilvan asks you, how do you see the Chinese CEPC initiative? Good competition?
Yeah, it is certainly good competition. On the paper, aside from minor details, the two projects are similar. It's good competition because they show the Chinese government, the fact that we are engaged shows the Chinese government that what the Chinese scientists are trying to sell them is indeed a frontier research enterprise. On our side, it's useful to know that China is pushing for this because, of course, it threatens the leadership of CERN, so we can use the argument with our politicians, look, if we don't do it, the Chinese will do it, and then, CERN risks evaporating. So I think it is a positive competition. It is a healthy competition because it keeps a bigger community, and the Chinese community is immense, as you can imagine, or will become immense very soon. And we are both engaged in thinking about the physics and certainly in trying to address the very complex technological challenge posed by these machines.
Okay, thank you. We have one more question from Rogério Rosenfeld. Hi, Michelangelo.
Hi, Rogerio.
Are there any plans to run E+ E- machine at the Higgs mass? There is a loop-induced single Higgs production that has a small cross-section, but it can be sensitive to new physics in the loop.
Yeah, there is a plan. It's been evaluated. And in fact, there was a paper on the archive that came out either today or yesterday, and you should be looking at it, from David Denteria and friends. And they've been studying in great detail the requirements of the machine. This is something that only the circular E+ can do, because only at the circular E+, you have the proper energy, control over the beam energy. Of course, the Higgs is a very, very tiny, small width, has a very small width, and therefore you have to control the energy of a beam with great precision. Otherwise, you dilute the peak, you will never see it. So yes, it's been considered. The sensitivity which is projected now is at the level of a couple times the standard model value, which means that if you have deviations larger than a factor of 2, you would be sensitive to that. Okay.
Thank you, Professor Mangano. We actually have one more question. As we have time, oh no, okay, it's just thanks. Rogério is just thank you. Okay, so thank you again for your talk, and then we can move on to our next speaker, that is Professor Ignacio Bediaga. Are you ready, Ignacio?
Yes.
Okay, so let me introduce you before. Ignacio Bediaga graduated in physics at the Pontifical Catholic University of Rio de Janeiro in 1980, then got a master in physics at the Brazilian Center for Physical Research, CBPF, in 1982. And after that, a PhD in physics at Universidade de Torino in 1987. He is currently a full professor at CBPF. He participated in many experiments at Fermilab and is now a member of the LHCb collaboration and the team leader of the LHCb group at CBPF. And I have to add that he was my master advisor. So Ignacio, please.
Let me tell. I have problem with to compartmentalize the.
Okay. We have time. We have time. If you need some help.
Oh, is there something wrong? Not. It's okay for you.
Okay. It's appearing.
Okay. Thank you very much. Okay. Let me talk. Just to thanks to invite. It's a pleasure to talk again in the LISHEP, and I think it's the first time as a LHCb member. So thank you very much for the organizer. I'd like to talk about the highlights in LHCb. I just talk quickly about the collaboration, and then I enter in 3 different approach in physics that we are working in spectroscopy, CP violation, and radio decay, and then about upgrade and remarks. LHCb collaboration has more than 1,000 authors. It's about 1,500 members and 88 institutes, 19 countries, and more than 500 physics results. It's a long-term project. We beginning take data in 2010. Now we are in 2021, just finishing the first upgrade to begin the run 3 that probably finish in 2013, and we believe with 50 investors Ventobar. The performance after the run 1 and run 2, LHCb and LHCb, we record 9 inverse of Ventobar. Run 1 with 7 and 8 TV, and run 2 with 13 TV. Proton lead, and the proton gas, that's a fixed stagger runs. We get some And LHCb is a multi-purpose forward detector. By the way, got exactly this luminosity that hinted in the time of the techno proposed in 1998. It's a forward spectrometer, how you know. The tracking system performance was very good during these 2 runs, with a high efficiency in reconstruction, good momentum resolution, decay time with 45 femtoseconds. And also we have a particle ID performance very good, with UID 97%, KID 95%, and also in the electron. The typical LHC event is in this cartoon. You can see a lot of events in forward direction and a few events in transverse momentum. So the LHC has 2 kinds of detector. One that CMS to look at the high PT, and LHCb to forward direction. How you can see in this cartoon, there is a lot of tracking. So what is the strategy of LHCb doing physics? The idea is to have a very good separation between the primary vertex and secondary vertex. Remember that charming beauty has a lifetime around 1 picosecond. And with this good separation, primary and secondary vertex, we have been doing a lot of beautiful physics. In hard decays, you just publish B-sub in 2 millions. It's a branching ratio of 10 to minus 9. That's the signal. And with more than 10 standard deviation. So a very clear signal with a branching ratio 1 billion decays. We have managed with millions of events. By the way, billions of events, but in particular this decay, the 0 in K short by plus by minus, that's a beautiful Dallas plot with 51 millions, and also a very precise measurement. This is also a new result of the B-sub in DS pi, looking at the oscillation, the BS bar oscillation with a very detailed behavior of the oscillation, and get a real good delta MS. If you look at the idea of the main laws of nature and cosmos, this is the cartoon vision of the high energy physics, US high energy physics. We in this cartoon are in the intensity frontier. And the intensity frontier LHCb means that we are able to be in the very good measurement in CPV, CKM, rare decays, spectroscopy, KCD, electroweak, lepton university, heavy ion, and also in hadron interaction. Well, let's go to the physics results. The spectroscopy, Patrick Koppenburg will talk later, a long and beautiful presentation. I just point out some things that I'd like to in complementary way to the Koppenburg. Well, that's the very known new hadrons found in LHC. In fact, there is 59 hadrons found so far, and it's still counting. But I'd like to point out how we can observe new particles. There are two different ways. One is very clear, very old, and the people are very use this. This one is the direct proton in collision. The simple way is the electron positive annihilation, goes to zero, it go to plus or minus. You have a big amount of events in Atlas, and you have this beautiful signal, and you can say that you observe the Z0. Another one is more recent, is the Higgs. You have proton-proton collision. The proton-proton collision produce the Higgs, and the Higgs they can gamma-gamma, and you observe these two peaks. But there's a different way to observe new particles. This different way is going to B, D, or lambda B decays, lambda C decays, and in 3 or more particles, and look at 2 of the 3 particles. This cartoon, you have for example, the B goes to DDK plus, DDK plus, but if you look at the KD invariant mass, you can you can see a peak. It's wonderful because you have the separation of the B and D in this a lot of events in forward direction, and look at the B, and you can see here the signal of B. There's almost nothing in background, so it's a very good way to observe. But you have a problem with this. You have, together with the channel we are looking for, there's another channels that you have to sum in a coherent way, since you have the B and the initial state and the final state is the same. So you have to a coherent sum, and you have to disentangle the different contribution necessary through the amplitude analysis, that it is not, it's a model dependent. So we have to be careful when you look at this channel. Let's start talking about the T4C. That's a beautiful result in LHCb in the method 1. So looking at the collision, we produce a collision proton-proton, and look only to the case with an event with 2 J psi's. That's the mass distribution. This is the scatter plot. We collect 33,000 events, and we have to understand if they come from the single particle scattering. That means a resonance or a particle produced by two partons goes to J psi, 2 J psi's, or double particle scattering goes to 2 J psi, but in a non-correlated way. How you separate this? Looking from the transversal momentum. If you can see the transversal momentum for all, there's nothing, just a continuum. But if you increase the beams of momentum transversal, you can see some structures. In fact, when we take the distribution from PT bigger than 5.2 GeV, we can see this beautiful figure with 1 peak and the dip. We test in principle, the double parton scattering must produce a non-correlated way, so you expect a continued distribution of the eventos. But when we fit with this continuum distribution, we observe that it's not working. So it doesn't work and with more than 5 sigmas. So we try to solve this problem with 2 different approaches, but with similar chi-square. So we are not able to decide what's the best solution. But both solutions have 2 resonances, one non-interfering with this mass and this radius, and another contribution is 2 resonances interfering, but have basically the same mass and a little bit more width. So it's clear in our point of view that we discover a 4 theta quark with 4 C quarks. Another example, but in this case, in the second method, we look at a new particle, but looking at the B plus and D plus, the minus, K plus. We collect 1,300 events with a high purity, 99.5%, let's see. And we put the Dallas plot. The Dallas plot, the mass squared D in one side and mass D minus K plus in the other side. In the mass of the D, you can see 2 clear resonances in around 15 GeV. One is the key C2, and the other is PC that you can see here and goes to DD. But for the other side, if you look at the D minus K plus, you can see that's some structure. In fact, this structure, but in fact, when you integrate in DD mass, you can observe a peak around 2,900 events. We perform an amplitude analysis with all resonances we know, and at the end, we cannot explain the existence of this peak. Only when we include the path. So, sorry, just a moment. Only we include 2 new resonances. In this case, also a theta quark with mass 2,900. We can fit well our peak in this mass region. In principle, this theta quark is the first one that has the 4 quarks difference. Okay, it's amazing to think in a 5-9 hadrons found LHC, and it's also nice to see that 17 of these are exotic. So LHC is a machine to produce exotic in principle. And but if you look at the 17 exotics, you can see that 15 of them were observed from disintegration of heavy particles. So the second method. Only 2 were observed directly in collision. I think it would be nice to understand better what this means. This exotic is to look also in observe directly in collision. So in collision, I think it will be important to confirm and to understand these 17 new exotic particles. Well, let's go to CP violation. CP violation, the equation of CP violation is very low, but just to remember, to have CP violation, you have to you need 2 amplitudes these amplitudes must have different weak and a strong phase. These equations, you can see that directly from the equation. This one. The phase phi change conjugate, so weak phase that we believe come from CKM, and the strong phase change, no change signal, and it's no strong operation. Our physical observable is the difference between the number of particles come from the particle and minus the number of antiparticles in a decay over the sum. Let's go to present wonderful results from LHCb, looking from the 0 kk and the 0 pi decays. The 0 kk, you have 4 million events, and the 0 pi 14 millions. Our observable, for some reasons, experimental reasons, was the difference between the two ACPs. And at the end, we have this 15.4 plus minus 2.9, 10 minus 4, with 5.3 standard deviation from 0. It was a negligible contribution from D0 bar, so we can classify this as direct CP violation. There's a lot of media involved this, but I think it's important to open a new window to explore CP violation source in their consequence in time decay, how Maurizio Martinelli will talk soon. But let's go back to this to the CP violation by looking at the strong phase. The strong phase, people think only in the weak phase, but a strong phase is very important. It's fundamental, and it's very important to understand the source of the strong phase. There's two ways to believe that the origin of the strong phase. One is very, very old and well established, is Brande Silverstone PSS at quark level in 979. The idea is you have a three component for the case. B goes to, for example, K pi or so on, and also a penguin contribution. And this penguin contribution is able to give the strong phase to have the CP violation. The another philosophy and is the strong phase come the hadron rescattering. So you have, for example, B goes to K pi, but the K pi goes rescattering the K0 pi 0 and K minus 4 and so on. And the idea is, of course, we have the three component with weak phase, but the strong phase come, for example, if you have a particle goes to alpha, but you have the particle goes to beta, and beta rescattering and finish alpha. These two contribution interfere and create CP violation. Again, well, so in two-border decay, you cannot discriminate one from the other. What strong phase is created with CPV. So let's go to three-border decay. We published many years ago results looking at the ACP beam by beam. So each beam has this ACP. You can see the four decays we studied: K pi pi, KKK, 3 pi, and KK pi. And you can see the green no CP violation, blue positive CP violation, red negative CP violation. You can see in one decay positive and negative CP violation in the same decay. Look at the B3 pi is amazing, that amount of CP violation, but with positive. When you integrate, it's not so big, but inside there is a big amount of CP violation, the B and KKK and so on. So recently we look at this CP violation using amplitude analysis. Just to remember, in 2000, with data of 2010-2011, we able to observe the CP violation. This is the PKK in KK pi. This one, if you look at the decay, you can see this huge CP violation. When we use the total run one data, it was confirmed. But recently, we produced an amplitude analysis. And in this amplitude analysis, other than the resonance particle that's normal to be there, we include an amplitude. By the way, an amplitude in the producing the 8s to KK in pi pi. And we get a good agreement from this amplitude to explain. You can see the fit very well. And with a huge CP violation, that's the biggest CP violation observed in a single particle, 64%. When you look at the 3 pi, also, it was published last year. The big CP violation involving sigma and F2, you can observe a big amount of CP violation in both. But when you look at this circle, around this circle, you can see a red, so a positive and negative very close to each other. And in fact, when you look at the interference between the S wave with P wave, that means the interference between the sigma and the rho, we can observe a very high CP violation. In fact, we look the significance of the CP violation observed was 50 sigma. So it comes from the hadronic interference between two different waves. Well, the conclusion is that both results show that the strong phase for CP violation has important, the strong phase for CP violation component hadron interaction. Well, Harold case, this result, it was produced the first time together with CMS. Now LHCb continue to take data and analyze this decay, BS in MIMI. We use 2 channels to normalize, and sorry, this one should be here. We observe now with 10.08 sigmas a channel -9. And then that's the signal. And here is the standard model together with the results. The results of the BS is quite close with standard model prediction. The B0 in mu plasma minus is approaching to be observed in the standard model. There is a historical endeavor from this saga with more than 30 years. That's a beautiful collection of the measurements. It's beginning before the 90s, and is coming here. In the middle of 2010, we observed the BS, and this is falling, and probably we are approaching to arrive to be a B0 in plasma minus.
Next, 5 minutes, okay?
Okay, perfect. The LHCb has a extensive program looking at the B goes to S lepton, looking at the ratio, angular asymmetry, branch ratio, lepton flavor violation, search, and lepton flavor universality. That's we'll talk the next talk. Let's only to present one result. I think it's beautiful. Just present by the collaboration is the differential branch ratio in chi-square for the BS in 5 mu plus minus decay. Here you can see the total amount of events, but it includes J-psi and psi 2s. So when we cut these events from this sample, we observed 2,000 events in the invariant mass of the 5 mu plus mu minus. For each chi-square, we plot for the branch ratio for each chi-square. You can see this figure, and we compare with some theoretical approach, and there is some difference between the expected by theory and experimental result. By the way, similar that the other results that we presented before. So there is continued this tension between theory and experimental in this kind of physics. Well, the upgrade was, oh, sorry, there's a huge change in the LHCb. This project has more than about 10 years. And the idea is to adapt to high increase of the luminosity. And we have to prepare to a 40 megahertz readout, so completely new electronic. And at the end, almost a new detector for round 3. We have new silicon tracker, new vector localization, new mirror for the photon detector, and new scintillator fiber track. This we contribute in this project, and new readout electronic photonic detector. I think one very important to say in this upgrade is the change of the trigger. Our previous trigger in run 1 and run 2, there's a low hardware trigger that's not so efficient. And now we have a trigger complete in software with 2 different technologies, GPUs and CPUs. At the end, we think to collect more than 10 times than the run 1 and run 2. The schedule, you know, that we are finishing to install the detector, and we intend to work for about 10 years with this detector, with some modification, of course. But at the end, we have multiplied by 5 our luminosity, integrated luminosity. The pixel value is here. It's a new one. Reach with new optics is plotted here. The UT also change in the strips. And here is the sci-fi with a wall of sci-fi. With at the end, using 11,000 kilometers of scintillator film. And here is the electronic we need. Oh. Just to remark that collaboration made, I think, a beautiful work in run 2 with high statistics, looking, observing 10 to minus 9 branch ratio. And it's able to work in different subjective intensity frontier. In the spectroscopy, it has a huge contribution from this 5-9 hadrons observed. I just talk about the 3,4C and theta quark. In CP violation, we observe first time in charge decay, and in three-body decay, you have shown a big contribution from hadronic strong phase. That's the first time observed in the dynamic of CP violation. In hard decays, you measure the branch ratio, the mu plus mu minus in 10 to minus 9, and many BSLL decays observed. I think we published 10 papers the last years, and with these new results. The upgrade starts at data taking and beginning next year. Okay, that's all. Thank you.
Thank you, Ignacio, for this very nice talk. We have one question. Rogério is asking, what's the Brazilian contribution to the LHCb 1A upgrade?
Yes, in two different ways. One in our group, led by Massaferri, was the scintillator, sci-fi. It is, let me see first. This sci-fi, the electronic of sci-fi was created here in CPPF, and the test, I don't know, but test all the electronic of the sci-fi. And the group from UFRJ participated in develop. Other than contribution from the trigger, the idea of trigger, to the prepared to the run 3 data taking, and looking at the trigger, the behavior of the trigger for the special channels. That's our contribution.
Okay.
By the way, Brazil has a large amount of people working at CB. That's also Universidade Federal do Triângulo Mineiro, the PUC, also people from the campus of Xerém.
Okay, Ignacio, thank you very much again. Then we have to move to our next talk, to our next speaker.
Okay, thank you.
Okay, yes. Okay, yes. So our next speaker is Luciano Musa. So he will talk to us about the LSC collaboration. Luciano Musa got his PhD. Let me introduce him, brief introduction. Luciano Musa got his PhD in physics from University of Cagliari in 1994. Held a postdoctoral position at the INFN from 94 to 1997. Then he has participated in many experiments of ELIX, NA48 and NA45, all of them at CERN, as well as Alice, where he is now. He is a staff of CERN since 1997. where he's currently a senior physicist at the experimental physics department. He has had many relevant functions and responsibilities at CERN, and the most recent is to serve as a spokesperson of the LC collaboration. He's author of about 500 publications in many scientific journals and has supervised more than 20 PhD students in physics or instrumentation. Okay, so please, Professor Luciano, you have the microphone now.
Thank you, Wagner, and hello, everyone. Let me put my slides in full screen mode and reduce also the size of this. Okay, so it is my great pleasure to present the ALICE highlights. I will talk about the status and the future perspectives. But first of all, let me thank the organizers for the kind invitation, with the hope to have the occasion in the future to attend an in-person edition of this meeting. This is the outline of my talk. I will give a very brief introduction on the experiment and the collaboration. Then we'll discuss a few physics highlights. Actually, yesterday you had two presentations on ALICE soft physics and hard probes, given respectively by David Kinelap and Marcelo Munoz. And I will discuss the upgrade activities for round 3 and also future perspectives. Before I do that, a few quick words about the ALICE collaboration itself. We're about 1,000 signing authors coming from 173 institutes from 42 countries, including Brazil, which participates in ALICE with 30 members from 4 institutes. But let's say besides the numerical aspects, Brazil is a very important player in the ALICE collaboration, is really part of the backbone of the collaboration. Now, we'll very briefly introduce the ALICE detector, just maybe to remind you that we have the ALICE detector consists of a central barrel with the tracking, hadron, electron, photon, and jet reconstruction, which covers 2 rapidity units, and a forward muon spectrometer covering the rapidity range from -2.5 to -4. And in the first 10 years of operation of the LHC, we've been collecting data during runs 1 and 2 from all collision systems, from PP to lead-leads at various energies. And we have at the moment a little over 340 papers submitted. I will now start by presenting a few physics highlights with a focus on new results. And we start with our core business, which is the study of lead-lead collisions and the study of the confined phase of QCD matter, the quark-gluon plasma, which is formed when the energy density is larger than 0.5 GeV per cubic Fermi, value which is far exceeded in lead-lead collisions at the LHC and over a very large volume. Now, the results from lead-lead collisions cover a broad spectrum of measurements that address the various stages of the time evolution of the collision from the early phase, when the two colliding charged nuclei pass through each other and produce the high-density expanding quark-gluon plasma, to the hadronic phase that precedes the kinetic freeze-out of the final state hadrons. Now, I've tried to select a few highlights from our recent measurements, which are representatives of various stages of the time evolution of the collision, more than trying to make a review of the ALICE physics. So now a powerful way of studying the initial stage of the nuclear collision is via ultra-peripheral collisions, in which a photon produced by the strong electromagnetic fields of the nucleus interacts with the quark-antiquark pair from the partonic field of the other nucleus, producing a vector meson like ρ0, J psi, or the psi 2s. And we have performed the measurement of the production cross-section of the J psi and psi 2s. Here you see now the case of the J psi as a function of rapidity. And from these measurements, when compared, for instance, to the impulse approximation, which assumes no nuclear effects, allows extracting the gluon shadowing factor, which, for instance, it has at x of about 10 to minus 3, this value of 0.65. This is just to give an idea of the type of constraints we can put. But even more important is the first measurement of the J psi production as a function of the T Mandelstam variable, which is the squared momentum transfer between the photon and the target nucleus, which is sensitive to the transverse gluon distribution. So it provides constraints to the dependence of shadowing on the position of gluons in the nuclear transverse area. Now let me move ahead and talk about one of the characterizing features of the QGP, which is, of course, the color deconfinement. And the other prime tool to study it is quarkonia. And the suppression of the J psi charmonium state due to color screening in the QGP was observed at the SPS and RIC, and historically considered as one of the unambiguous signatures of the QGP. Here I show our results for the nuclear modification factor of the J psi in central lead-lead collisions, which reveals a completely different pattern, or pattern which is fundamentally changed at the LHC. At high PT, we have a suppression of a large suppression, a suppression of a factor of 5, which is described by models in terms of color screening and energy loss, while when moving to low transverse momentum, the suppression reduces. And this phenomenon is understood as the result of the fact that in a deconfined QGP, the charm quark, which at the LHC energies are producing very large number, copiously, can recombine, regenerating the charmonium state. And this is qualitatively in agreement with models. And this effect, which is seen only at the LHC and not at lower energies, is also supported by the fact that when we go to central rapidity, from forward to central rapidity, so from red to black in this plot, we see a larger effect, which is consistent with the higher density of charm quarks at central rapidity, as one would expect. Okay, so now the effect of the quark-gluon plasma on color charges can also be studied with the measurement of the upsilon mesons. So we measure the upsilon production at forward rapidity, and this indicates, again, a strong suppression of the interaction between the beauty and anti-beauty quarks in the deconfined medium. But as you can see here, the suppression is flat as a function of PT, indicating, again, as one would expect, because of course beauty production is more rare, so their density is much lower compared to charm. So indicating that recombination of BB bar quarks is small, and it is also well described by models. Let me also notice that you see this plot here where we're combining the results from CMS and ELIS. That of course, it is very nice to see this picture with the strongest suppression of the upsilon 2s with respect to the ground state, which is also consistent with this lower binding energy. So this is really a way of measuring hierarchy of melting of the quarkonia states. Now, let me continue with heavy quarks and their interaction with the medium. Heavy quarks, maybe I should have made this a small preamble, charm and beauty are very important probes to study the properties of the quark-gluon plasma formed in lead-lead collisions because of their large mass. So they are produced before the QGP is formed, and they subsequently interact with it, okay? And so the measurement of hadrons with heavy quarks provide information both on the interaction with the QGP, so the QGP properties, as well as the process of hadronization in presence of a high density of surrounding particles. Now, what you see here is actually something quite nice. It was anticipated nearly 20 years ago that when traversing the QGP, B quarks would lose less energy with respect to C quarks because due to their larger mass, they would radiate less at small angles due to the dead cone effect. And now we have measurements which are sensitive to this prediction. We measure the nuclear modification factor for non-prompt D0 mesons, which are in blue in this plot, and compare it with the one for prompt D0 mesons, which are in red. So they probe B and C quarks respectively. And we see that in the case of B quarks, there is less suppression, which is well described again by the models that implement radiative energy loss with the dead cone effect. Now, I'm showing here a new ALICE preliminary measurement, which uses machine learning techniques to discern the charm-strange mesons, the sub-S, that originate directly from the hadronization of charm quarks, so the prompt sub-S, and then from those that originate from the decays of beauty hadrons, so non-prompt sub-S. And the non-prompt sub-S are also compared with the previous measurements of non-prompt D0. Now, these preliminary results show that the probability of forming a beauty-strange meson in lead-lead collisions tends to increase with respect to that of forming non-strange beauty mesons, although this data is not yet fully conclusive. Again, the measurements is described by a theoretical model that includes hadronization of beauty quarks by recombination with U, D, or S quarks from the QGP. So building really a more precise picture of the hadronization mechanism. Measurements with the upgraded ALICE detector in run 3 will make these measurements and observation much more conclusive. Now, let me move to a few results related to PP collisions, not lead-lead collisions anymore. And this is related to a very exhaustive set of measurements that ALICE has performed of charmed mesons and baryon production in proton-proton collisions. So we measured the mesons, the charmed baryons, lambda 6, IC, the sigma C, and these measurements have enabled the determination of the total charm cross-section, production cross-section with an unprecedented accuracy, as well as the charm fragmentation fractions, in other words, the probabilities of the various charmed hadrons to be formed. And we found that these probabilities are not universal. So they are not independent of the collision system as it was assumed for a long time. The observed charmed hadron distribution in proton-proton collisions is very different from previous measurements at the electron-positron colliders or from electron-proton colliders. So, for example, the probability that the charmed baryon lambda C is formed is about 3 times larger in proton-proton collisions compared to E plus, E minus collisions. Now, these ALICE measurements have stimulated an intense theoretical activity for their interpretation, mainly in terms of hadron formation mechanism that take into account the surrounding environment of strongly interacting particles. These explanations include color recognition across the whole set of particles producing the collision, as well as the formation of hadrons by coalescence of the charm quark with other quarks and antiquarks created in the collision. Now, I have to run a bit faster here. So I mentioned before the Dedekon effect, and now this was for the first time measured directly by ALICE, studying the pattern of the parton shower in PP collisions, which is one of the key experimental tools to understand the properties of QCD. Now, this pattern is expected to depend on the mass of the initiating parton through the phenomenon which I already mentioned before, so the Dedekon effect, which, as I said, predicts a suppression of the gluon spectrum emitted by a heavy quark of mass m and energy E within a cone of angular size m over E around the emitter. So now a direct observation of the Dedekon effect in QCD was not possible, has not been possible until now, due to the challenge of reconstructing the cascading quarks and gluons from the experimental, from the hadronic states. And we made the first observation of the QCD Dedekon effect by using new iterative declustering techniques to reconstruct the parton shower of charm quarks. So these measurements confirm this fundamental feature of QCD. Moreover, this measurement also represents, in a way, a direct experimental observation of the non-zero mass of the charm quark. Now, the observable is this R of theta, which is built constructing the ratio of the splitting angle theta, so the splitting angle distributions for the zero meson tagged jets and inclusive jets in beams of the energy of the radiator, so in this case of the charm quark, and in beams of KT, which is given by this formula. Now, so the measurement of this R theta has been performed in 3 radiators energy intervals. You see from 5 to 10, 10 to 20, 20 to 35 GeV, and it clearly shows a significant suppression in the rate of small angle splittings in the zero meson tagged jets relative to the inclusive jet production. Now, let me mention, this is really the last topic, just to show also the breadth of the ALICE physics and more in general of the LHC. So this is about now, in a way, hadron physics. So the possibility of studying the QCD interaction between hadrons. We demonstrated in the past 2 to 3 years that measuring the correlations in the momentum space between hadron pairs producing PP collisions at the LHC provides a precise method to obtain the missing information on the interaction dynamics of any pair of unstable hadrons. So essentially what we measure is the correlation between pairs with a certain relative momentum difference. So we compare this with the pairs of uncorrelated particles. And this quantity is related to the size of the emitting source, to the wave function of the 2 interacting particles. So therefore, the experimental quantity we measure is the correlation function. The source size can be characterized independently. And therefore, with this, we can extract the misinformation on the dynamics between the 2 interacting particles. And for instance, we have been showing precision measurement of the proton like psi minus and proton omega minus correlation, which allow to determine very precisely the effect of strong interaction on these hadron pairs. So in other words, if what one takes is a potential, assuming only a Coulomb potential, then one calculates the correlation function. And you see that actually the data shows that on top of the Coulomb potential, there is an attractive potential, which is the strong, the effect of the strong force. Now we have performed a series of measurements. You see here all the ALICE publications on this topic. And now, and more recently, we're also extending this to lead measurements, not only to PP measurements, which is also very nice because with this, this allows essentially to vary the interparticle distance and therefore making measurements which are sensitive to inelastic channels, but also to elastic channels. And this is a good alternative to scattering experiments or other experimental approaches. Now, in the last few minutes, I would like to say now a few words about the preparation of the experiment for Run 3 and Run 4, what we call ALICE version 2.0. Let me remind you that in this moment we are completing a massive update of our detector, the preparation of which started nearly 10 years ago, and which enables a large improvement of the vertexing and tracking precision and efficiency, especially at low momentum. But more importantly, it enables a 50-fold increase of the event readout rate. This is, of course, quite a large factor, and is really going to help our physics program a lot as far as rare probes and a variety of other observables on which we cannot trigger are concerned. The key items of this upgrade program are illustrated here. So we have a major upgrade of our main tracking device, the time projection chamber, a completely new silicon tracker, a new fast interaction trigger, major refurbishment of muon spectrometer, and essentially an upgrade of the readout electronics of all detectors to be able to run in continuous mode, as well as a completely new integrated online-offline system based on a heterogeneous hardware platform combining CPUs and GPUs. Now, I've no time to discuss any of it in detail. Just let me remind you that the upgrade of the TPC with the replacement of multi-wide proportional chambers with GEM-based chambers, a completely new pipelined readout electronics based on the Sampa chip developed in Brazil by the ALICE team of Sao Paulo and Campinas, is the key item to increase the readout rate capabilities, essentially to be able to cope with the maximum lead-lead collision rate at the LHC of 50 kilohertz, reaching particle rates that would have been considered totally inconceivable for a TPC 20 years ago. The other main pillar probably of this upgrade program is the completely new inner tracking system, silicon tracker, which is based on monolithic active pixel sensors, which is composed of very lightweight modules with a record figure for material budget of 3.5 per mil. And essentially, we are moving from a system with about 10 million channels, just to give you an idea of the dramatic increase of granularity, to a system which will contain 13 billion pixels, while at the same time reducing the material budget of the innermost layers of a factor of 3. And that will lead to a major enhancement of the ALICE performance for the measurement of, for instance, open heavy flavor at low transverse momentum, as well as low mass dileptons. Now, despite of the difficulties and restrictions caused by the COVID outbreak, the LS2 upgrades activities have advanced well. Flashing here a few pictures that mark the most important milestones of the installation of the ALICE upgrades. You see here the TPC installation, which happened in the summer last year, in August 2020. You see here pictures of the installation of our Muon Forward telescope. This is a silicon telescope, as well as the seaside of the fast iteration trigger in December, just before Christmas. In January, we have completed the installation of our new online processing system, the system based on CPUs and GPUs. This is the new Alice data center. And in May, we have installed the new silicon tracker that was a very delicate operation because the innermost layers of the ITS goes at a radial distance of 2 millimeters from the very fragile beryllium segment of the beam pipe, and this has been completed successfully. And just a couple of weeks ago, we also have installed the last item, which goes inside the, which is part somehow of the central barrel. Though this, I mean, it's more a forward detector, but let's say it's completing the installations of our detector sequence installation. Now, the sequence of installation is essentially completed, and we are now about to start a period of 18 weeks of global commissioning with all ALICE detectors and the systems. This will continue till the end of November, and includes a period of the so-called pilot beam test, which is a period of about 20 hours, 10-20 hours, with stable collisions with the stable beams, but at the SPS injection energy, which is planned for the second half of October. And this plan has at present 3 months of contingency with respect to the LS2 end date of the 21st of February 2022. Now, this is for run 3, but things do not just stop there. For LS3, for 2025 and 2026, we have another exciting update of the ITS in preparation, which is going to involve essentially the replacement of the innermost 3 layers of the ITS with essentially truly cylindrical silicon maps layers based on a novel technology with much better performance. So this will be literally curved, wrapped around the beam pipe. Now, this will reduce the material budget by another factor of 6, and also it allows to go closer to the interaction point. So again, going in the direction of improving the impact parameter resolution and the tracking efficiency, in particular at low transverse momentum. This is in the works. You see here some pictures of prototype testing. The LOI is approved, and we are now working on the R&D in view of submitting a TDR towards the end of next year and bring this to reality in 2025, 2026. In addition, we have also plans for a forward calorimeter. We call it focal, which is going to be able to perform measurements of isolated photons at forward rapidities. And one of the things it can do is to constrain the gluon nuclear parton distribution functions with unprecedented precision below Bjorken X of the order of 10 to the minus 3 and all the way down to 10 to the minus 5. Also in this case, we have the LOI approved, and we are working on the TDR to get this done for run 4. Now, even beyond run 4, going towards 2031, a bit more distant in the future, we are preparing a letter of intent for what we call the next generation dedicated heavy ion experiment. We call it also ALICE 3, which is almost entirely silicon-based, ultra thin and fast, which would buy us another factor 50 in terms of luminosity, but would also have strong particle identification capabilities with the time of flight, reach, and pre-shower detectors. This will give us a significantly enhanced performance on the measurement of electromagnetic and hadronic probes of the QGP that will allow us to address a variety of physics questions, the mechanism of hadron formation in the QGP transport properties, the QGP electrical conductivity, the radiation emitted by the QGP, and including the access to the so-called pre-hydrodynamization phase, current symmetry restoration, etc. This initiative has received positive feedback from the European Strategy for Particle Physics update, and we are now preparing an LOI to be discussed with the LHCC in the fall. So we are much looking forward to have also this to happen in a bit distant future. And with this, I would like to conclude. I've presented a few ALICE measurements to show that we have a wealth of results that already came out in run 1 and 2, which allowed us to gain a detailed insight into the QGP, as well as make advances in QCD at high density. But as you've seen, this is not all. There is more coming up, and we're very excited that the LS2 upgrade is almost completed. We are on track to start the global commissioning this month. And also you have seen that we have more than that coming up during LS3. And we also have a more ambitious plan far ahead of us beyond Run 4. And that's it. Thank you very much for your attention.
Okay, thank you very much for your very nice talk. We have one question here. Gilvan, can you give more details on the fast integration trigger? Fast interaction trigger.
Yeah, okay, so that's a good question, because on one side I've mentioned that ALICE is moving towards a continuous readout, namely a triggerless readout scheme. And that is actually true for the vast majority of the detectors, in particular the silicon trackers in the central barrel, and also the forward silicon tracker, the time projection chamber, and as well as the muon spectrometer. However, there are a number of detectors which will be able to cope with the maximum lead-lead interaction rate of 50 kilohertz, but they need to be triggered. So the fast interaction trigger is essentially a detector which gives us information on the multiplicity and time of the event. That is also providing information for the time of flight measurement. And so that is, if you want, our level zero trigger. Okay, so it's a combination of silicon detectors and plastic detectors that will provide this information.
Okay, thank you very much again for the speaker. Now we have to move forward. Thanks. Our next speaker is, sorry, just a second, I missed my window. Okay. Next speaker is Dr. Richard Hawkins that will talk about Atlas highlights. Dr. Richard Hawkins did his PhD in Oxford, UK, and has worked as a CERN fellow and days fellow before becoming a staff research physicist at CERN. He has been a member of the OPAL collaboration at LISHEP and the Atlas collaboration at LHC, where his work focuses on precision standard model physics, particularly involving top quarks. He has held various coordination roles in Atlas, including physics coordinator, and now co-leads the Atlas luminosity measurement group. So, Dr. Richard, please, you have the microphone.
Okay, thank you. Can you hear me?
Yes, perfect.
Very good. So I will share my slides. Do you see the slides?
Yes.
Okay, great. So let's get started. So thank you very much to the organizers. It's my pleasure to be here at this virtual conference and present to you some recent highlights from the ATLAS experiment. And I'm going to focus on selected recent ATLAS results from the LHC Run2 dataset, passing through some Higgs physics, some precision measurements and rare Higgs decays, searches for heavy gauge bosons and lepton flavor violation, then some 4-top and single-top quark production measurements. And you see here a nice candidate event for the simultaneous production of 4-top quarks. It has one muon, which is the red track, and then very many jets and B-jets. Then I'll talk about a couple of supersymmetry searches, and then give the outlook for Run 3 and beyond. So in this talk, I can only scratch the surface, so I really encourage you to look at the ATLAS public results page if you're interested in more information. So the context for ATLAS physics at Run 2. So the LHC ran at 13 TeV from 2015 to 2018. And during that time, we accumulated a total of 147 inverse femtobands of data, PP data recorded by ATLAS. And you can see the progression here, mainly in 2016, 17, and 18. And of that, a very good fraction, 139 inverse femtoband, is good for physics analyses. You see this table of the performance of the various detector components and what fraction of the time they gave usable data. This data is characterized by quite high pileup. So this means the number of simultaneous proton-proton collisions that happen in one bunch crossing. That has a distribution shown here, which is different for each of the data taking years, goes up to about 60 or 70 in 2017 and 18, and has an average of about 33.7. So it's quite a harsh environment. But despite this, we've managed to make a precise calibration of the physics objects. So for example, lepton efficiencies for electrons are understood to less than 1%, and for muons to 1 part per mil. The jet energy scale is understood to 1 to 3% for jets with PT greater than 30 GeV. And we've just celebrated the milestone of 1,000 ATLAS collision data papers, and there's a nice timeline if you want to click on that. And we have now 135 results on the full Run2 dataset. So I'm going to highlight some of these results, new physics searches and standard model measurements, and try to showcase some of these measurements and searches. So let's start with the Higgs. So a quick review on the Higgs. The Higgs-like boson, as everyone knows, was discovered at the LHC by ATLAS and CMS in Run 1. And the big question is it the standard model Higgs boson, or is it something else? At Run 2, we're focusing on measuring its properties. So one area is to look at the different production modes. The Higgs boson can be produced in different production modes, such as gluon-gluon fusion, vector boson fusion, where 2 vector bosons are produced radiated from initial state quarks, and then they fuse to produce the Higgs. Or we can have associated production of a W and a Z, sorry, a W or a Z in association with the Higgs, or it can be produced in association with top quarks. And this plot shows the ratio of the measurements in all of these different production channels to the expectation according to the standard model predictions. And you can see that all of these predictions cluster around 1. So the Higgs is being produced more or less as we expect. We also look at the Higgs decays into bosons. We've seen the WW, the ZZ, and the gamma-gamma decays, and also the decays into 3rd generation fermions, both BB bar and tau-tau. And we're now in particular looking at the 2nd generation fermions. So for example, the dimuon final state, where we have some first evidence for that, and also now what I'll talk about in a minute is the decay of the Higgs into charm quarks. This plot on the right shows the reduced Higgs couplings for the different particles as a function of the particle mass, and you see it forms a nice straight line on this log plot, which shows that the Higgs couplings have the expected dependence on particle mass, if as you would expect if the Higgs has something to do with the generation of mass. Then the CP properties of the Higgs have also been studied, and so far they've come out more or less as expected. So let's go for Higgs to CT bar, charm decays. The dominant decay of the Higgs boson is to BB bar, and the branching ratio is 58%. That was observed in 2018 via the associated production modes WH and ZH, where the W or Z decays to leptons and the Higgs to BB bar. So the search for Higgs to CC bar follows the same path, but it's much more challenging. First of all, the branching ratio of Higgs to CC bar is only 2.9%, so much smaller than BB bar. It's also much harder to tag charm jets than B jets, but we do have a rather performant charm tagger now available, and we can pick out the intermediate lifetime charm hadrons from the background somewhere between the longer lifetime B hadrons and the prompt jets from light quarks and gluons. So you see here the charm tagging efficiency as a function of the jet transverse momentum PT, and you can see in green we have about 27% efficiency for tagging charm, compared to about 8% for B, shown in red, and 1.6% for light quarks, shown in blue. And these efficiencies have all been calibrated using the data. So in this analysis, we select events with large missing energy, or 1 or 2 leptons, to select the W or Z bosons, and then we require 1 or 2 charm tag jets. We veto B tag jets, and then we look at the invariant mass of the 2 highest transverse momentum jets, which we assume to come from the Higgs decay. So from the signal, we'd expect to see a wide signal peak. It's rather wide around the Higgs mass of 125 GeV due to the limited jet resolution. And this sits under a big background from W plus jets, Z plus jets, and top. On this plot, the Higgs to CC bar is multiplied by a factor of 300, so you can actually see it. So this is quite challenging, but we have been lucky that nature gives us a natural calibration signal from diboson production, V equals W or Z. So for example, a W or a Z and a W decaying to a charm and a light quark, or a W or Z produce an association with a Z decaying to CC bar. So these signals give broad mass peaks around the W and Z masses. So this plot shows the data with all of the non-diboson background subtracted, and you see you have a nice signal for these diboson signals, and then we look at the roundabout the Higgs mass and see if we see anything there. So we do a simultaneous fit to all of the signals. The signal strength is fitted. It's denoted by mu, which is the rate normalized to the expectation in the standard model. And you can see we fit mu for this WZ and VW and VZ. Mu values are fitted close to 1, and we have nice significant signals for both of these calibration measurements. And then we looked around the Higgs mass, and we actually fit a negative mu for the Higgs. So we actually we favor a slightly negative Higgs to CC bar signal, shown by this red histogram tiny red histogram under the line. However, the data is such that mu equals 1, which would be the standard model prediction, is certainly very compatible with what we see. What we can say is that at 95% confidence level, the Higgs to charm production is less than 26 times the standard model. So that's shown by the line histogram there. So we can set an upper limit on the Higgs production in this the Higgs production decaying to CC bar at 26, compared with 31 expected from this analysis. And we can then use that as a limit on the Higgs to charm coupling modifier, shown on this log likelihood plot here. We can say that this coupling modifier kappa C is smaller than 8.5, assuming that the modified coupling only affects the Higgs to charm decays, not the production. Moving from rare Higgs decays to precise measurements, we can look at Higgs decaying to WW star, which then decays to an electron and a muon and 2 neutrinos. And this is a very nice decay mode that allows studies of the different Higgs production modes. So for example, gluon-gluon fusion, in this mode, we just produce the Higgs, and if we have any other jets in the event, they must have come from initial state radiation. Contrast this with the vector boson fusion production mode, where you have these 2 bosons, Ws or Zs, being radiated from initial state quarks. They fuse to produce the Higgs. So we see an event with a Higgs boson and 2 forward quark jets that have large invariant mass and large delta Y rapidity separation. The background in both cases comes from continuum WW star production and top pair production, and we can exploit the opening angle in the transverse plane delta phi between the electron and the muon, which tends to be smaller for the Higgs signal due to the spin zero nature of the Higgs boson. So we can separate the different production modes using the number of jets and a dedicated deep neural network for the vector boson fusion channel. Backgrounds are estimated using control regions for all the major backgrounds. For the gluon-gluon fusion mode, the final discriminant is the transverse mass of the dilepton system. And you can see once we subtract the backgrounds, we get a very nice Higgs signal, which contains several thousand events showing up as shown in blue in this background subtracted distribution. There's also a nice signal in the vector boson fusion mode seen in this background subtracted deep neural network distribution shown in orange. So we can make a simultaneous fit to both the signals. This is shown on here. The y-axis shows the gluon-gluon fusion, the x-axis the VBF, vector boson fusion production. And you can see with this ellipse, the black point on the ellipse is at 68 and 95% confidence level. We have a nice signal, which is in nice agreement with the standard model prediction shown by the red cross and ellipse. So in particular, the vector boson fusion production mode is now observed with a 6.6 sigma significance. We can then go further and look at the details of the different production modes, and this is done in the so-called simplified template cross-section framework, or STXS. And here we make measurements of fiducial cross-sections in different production modes with different jet multiplicities, with different Higgs and jet kinematics. This is a well-defined framework which has been agreed between the experimental and theoretical communities for characterizing Higgs production. And these categories map nicely onto the experimental selections or bins that we make to separate the different production modes. So again, you see this plot with all the different categories, and you see the experimental measurements divided by the standard model prediction, and again they all cluster around 1. So there's a good overall agreement in this channel between how the Higgs is actually produced, how we measure it, and how it's expected. And the p-value for compatibility with the standard model is 52%. Going towards the future of Higgs studies at the LHC, we can start to look for di-Higgs production. So the di-Higgs production, 2 Higgs bosons in the final state, is sensitive to the Higgs self-coupling through this diagram here on the left. And we have a coupling kappa lambda, the coupling strength modifier, which we can change to parameterize deviations from the standard model prediction for this diagram. Unfortunately, this is not the only way that di-Higgs can be produced. We also have this box diagram on the right, and unfortunately, these 2 diagrams interfere negatively. So we have destructive interference, which means the cross-section in the standard model is only 30 femtobarn for this process. It's quite rare. But we can go out and look for it. One of the most sensitive channels is where 1 Higgs decays to BB bar and the other to gamma gamma. So this combines a high branching ratio BB bar decay and a very clean, but unfortunately low branching ratio gamma gamma that we can use to trigger on. So we make a boosted decision tree selection using kinematic variables. You see here one of the selection regions here. This is the gamma gamma invariant mass spectrum. So we'd expect the Higgs to show up about 125, as shown by the expectation in red. And you can see the main background is from continuum BB gamma gamma production. So at the moment, we have only a handful of events. We don't see any significant evidence of di-Higgs production, but combining this selection and other selections in this analysis, we can set a limit at 130 femtobarn at 95% confidence level, which is about 4 times the standard model expectation. We can then look to see how the Higgs, the prediction for di-Higgs production would vary as a function of kappa lambda, and we can then set limits on this parameter where this intersects the observed limit. So we can say that kappa lambda is between -1.5 and 6.7, where the value expected in the standard model is 1. This analysis has also set limits on resident di-Higgs production, where you have a beyond standard model particle decaying to 2 Higgs bosons. And this, of course, will be a key topic for Run 3 and the high luminosity LHC as well. We can also, now the Higgs has been discovered, we can also look for new physics, new particles which decay to Higgs bosons. So for example, some dynamical symmetry breaking models, such as composite Higgs models or Technicolor, predict that there will be new vector bosons, for example, W prime, that decay to Higgs. So for example, we could have this W prime to WH decay. We search for this by looking for the W boson decaying to an electron or muon and a neutrino, and the Higgs decaying to BB bar. So our final state we look for is lepton plus ET miss. and then either 2 resolved BTAG jets if the Higgs momentum is low, or one large radius jet where the 2B quarks from the Higgs end up in one collimated jet, which has 2 BTAG tracked jets within it. So this plot on the right shows the acceptance versus the W prime mass, and in green you see the acceptance from the resolved topology that fades out at high mass, but then the blue, which is the merged topology, takes over. So you see on the bottom left a couple of data distributions from this analysis for the resolved and merged topology, and you can see the data shown by the black points is in very good agreement with the expectation from standard model physics processes, and we don't see any hint of W prime production. So we can set limits on the W prime cross section times the branching ratio to WH, as shown here, and where this intersects predictions of a couple of models, we can then set mass limits on these heavy vector triplet models at about 3 TeV. We can also look for W primes decaying to fermions. For example, in the sequential standard model, we have a W prime, which is more or less a copy of the standard model W, and it decays equally into all the lepton flavors, electron, muon, and tau. But we can also have models with enhanced couplings to tau, for example, the non-universal gauge interaction model, which can have an enhanced tau coupling if this parameter cot theta nu is greater than 1. So we can look specifically for decays of a W prime to tau. And to do this, we search for events with a hadronic tau candidate and large ET miss. So we identify hadronic taus in the detector as narrow jets using a recursive neural network and can get about 75 to 85% efficiency. And then we use the transverse mass, MT, of the visible tau decay products and the missing energy as a discriminant. And you see on the left, bottom left, a distribution from this analysis. And you can see again, the data is in very good agreement with the expectation from standard model backgrounds. We don't see any hints of W prime production. So we can set limits, first of all, in the sequential standard model shown in this middle plot. So we can set limits in terms of the cross-section times branching ratio, and where this intersects the prediction from the sequential standard model, can set mass limits. So we have mass a limit of up to 5 W prime up to 5 TeV are excluded by this data set, compared with the previous analysis on a partial run-2 data set in blue, which only excluded up to a bit over just under 4. We can also set limits in this non-universal gauge interaction model, and these are between 3.5 and 5 TeV, depending on this parameter, theta nu. So moving now on to lepton flavor violation. So the conservation of lepton flavor is accidental in the standard model. It seems to happen, but there's no underlying symmetry which would make this so. And we know that it is violated in the neutrino sector in neutrino oscillations. So one proposal is heavy neutrinos, additional heavy neutrinos, which could cause the Z to undergo lepton flavor violating decays, for example, electron or muon plus a tau at the level of about 1 in 10 to the minus 5 Z decays. So we search for this process, looking for the tau to decay to a muon or electron and 2 neutrinos. So the signature here is an electron and a muon, lots of ET miss, with the total invariant mass of these things coming back to the Z mass. So we look for back-to-back leptons in the detector with the ET miss collinear with the lepton, which we think comes from the tau. The main background for this is standard model Z tau tau decays to E mu plus 4 neutrinos, and then also top pair dibosons and events with fake leptons. And we use neural network classifiers to distinguish the different event types, and then we fit the data distribution of this neural network classifier to the standard model background expectation and a possible signal. And you can see, unfortunately, the data looks very much like the background. So we don't see a significant signal, and we set limits, which are about at the level of 8, 10 to the minus 6. We can then combine this with a previous analysis which used hadronic tau decays, and we get limits about 5 times 10 to the minus 6, as shown here, depending on the assumption about the tau polarization. And this surpasses now the limits from LEP, which are at the level of 1 10 to the minus 5. So now moving towards away from these searches now to top production. So we can now look for the process of the simultaneous production of 4 top quarks, two quarks and 2 anti-quarks, which can come about by gluon fusion diagrams, gluon-initiated diagrams such as this one, but also as a contribution with a virtual Higgs production, which then decays to TT bar. And this is sensitive to the top Yukawa coupling to the Higgs boson. There are also very many beyond standard model processes which can lead to 4 top production. Now, the standard model prediction is about 12 femtobarn, so again, a rather rare process. The top quark always decays to a W boson on a B quark, so there's lots of jets and B jets, and if the W's decay leptonically, then we also get leptons. So we can classify these decays according to the number of leptons. So 13% of the events produce a final state with either 2 same sign leptons or at least 3 leptons, and this is a low statistics process. The background mainly comes from top pair production in conjunction with a W, Z, or H boson or fake leptons. Or we can look at another category which has 57%, which is simply 1 lepton or 2 opposite sign leptons. The background here is top pair plus jets, especially B jets. So this first category was used for initial run-2 analysis, where in addition to the 2 same sign or 3 leptons, we also ask for at least 6 jets and 2 B-tag jets. We use a BDT using kinematics and B-tag information. Control samples are used to measure the TTW and fake lepton backgrounds. You can see here the results. And as we go to the signal-rich part on the right of the BDT score, close to 1, you see a nice excess for the production of 4 tops. We again characterize this via signal strength mu, the ratio of the data result to the standard model, and we measure mu equals 2 with an observed significance of 4.3 sigma. So this is about twice the rate expected in standard model, however, still compatible with the standard model within the uncertainties. We followed this up with a further analysis in the other channel, 1 lepton or 2 opposite sign leptons, where we again require a large number of jets, and we divide the data into bins of jet and B-jet multiplicity. We have a reweighting scheme with various control regions to improve the top pair plus B-jet modeling. The final discrimination is done with a number of per bin boosted decision trees using kinematic and B-tagging information. And this plot shows all of the different signal regions ranked according to their signal over background ratio. So again, the most signal-like, the best signal to background ratio ones are on the right. And again, you start to see hints of a signal building up. And the best fit value from this analysis is also mu equals 2.2 in this case. And the largest systematics come from the modeling of the 4-top signal itself and the modeling of TT bar plus BB bar. The combination of the 2 analyses is shown here. The final result gives mu for TT 4-top production of 2, with the errors shown here. The observed significance is 4.7 sigma, so almost 5 sigma, whereas we would expect only 2.6 sigma in the standard model. So we're measuring a cross-section which is a factor 2 higher than in the standard model, but it's consistent within 2 standard deviations. So I think this is very interesting, and it will be interesting to see how this excess develops in run 3. Now going to a more standard model measurement using single top quark production. So single top quarks can be produced, for example, in the T channel, where there's an exchange of a W boson. The dominant process starts from a U valence quark in the proton, and you produce a D spectator quark and a top. There's also a subdominant process where you have a D bar anti-quark from the C. That also produces a top quark. And the V-A form of the WT vertex in these diagrams implies that the spin of the top quark is always aligned along the direction of the down type quark, be that in the final state or the initial state. And you can also imagine the reverse diagrams, the charge conjugate diagrams, where we produce an anti-quark. We flip the signs of all of the quarks. So if we use the outgoing spectator quark as a reference direction, Z, we expect that if we produce a single top quark, it will be polarized mainly along the spectator direction. And if we have an anti-top quark, it's mainly against the spectator direction. So we can measure this from single top events in the lepton plus jets channel. we reconstruct the decay angle distributions, and this gives the information on the original top polarization, as shown in this picture here, where we have the polarization along this axis Z, along the spectator direction, versus the polarization orthogonal to that direction. And you can see for the top quarks, they are indeed polarized very strongly in the direction, and for the anti-top quarks, very strongly against the direction of the spectator quark. So this is polarization as expected. We can also use this data to gain sensitivity to effective field theory operators at the WTB vertex and use it to constrain possible new physics. So here you see one of the cos theta and angular distributions, and we can set limits on Wilson coefficients as given here. Moving now to supersymmetry, I want to just show a couple of searches. So despite a huge amount of searching at the LHC for supersymmetry, we haven't found, for example, any evidence of strong supersymmetric production, quarks or gluinos. And one of the focuses now is on searching for electroweak enos, i.e. the superpartners of the standard model gauge bosons. So these have rather small cross sections, and what we expect to see is, for example, a heavy charge eno or neutral eno, which would then decay, giving off a standard model gauge boson, a WZ or a Higgs, and then decay to a lighter neutralino, the lightest neutralino, which would then disappear as missing energy. So since most of the highest branching ratios for Ws and Zs and Higgs are into hadronic final states, it's good to try and exploit the hadronic decays to get the highest reach, highest sensitivity to this kind of supersymmetry signal. So we can use jet substructure techniques to reconstruct the boosted decays as a large radius jet, possibly with B tags if it's a Z or a Higgs boson. So the final state here is lots of missing energy plus 2 large radius jets, which are tagged with jet substructure as a WZ or H. So you can see here all of the different categories with different types of hadronic jets. The dominant background is coming, shown in blue, is coming from Z plus 2 Z decaying to neutrinos plus jets. And you can see there's no significant excess in any of these. So we can set limits, for example, on this model where you have pair production of a charge eno and the next to lightest neutralino decaying to standard model bosons and the lightest neutralino. So these limits, as a function of the mass of the lightest neutralino and the mass of the heavy objects, go up now into the TeV region, compared to what was shown in blue, the exclusion from the same data set using leptonic decays of the standard model gauge bosons. So this is just one example. This analysis note also considers many different supersymmetry signal models. The last analysis I'd like to show is a search for metastable particles. So this means particles that decay with lifetimes between microseconds or even years after they're produced. So this kind of phenomenology can arise, for example, in split SUSY models, where you have very heavy squarks and leptons, and only the gluino is at the TeV scale, and it consequently has a very long lifetime. So if such gluinos are produced, they could actually hadronize with standard model quarks and gluons and make R hadrons, which then travel out through the detector and get stopped in the calorimeter, and then they decay into, for example, 2 jets of particles. And so what we want to look for here is out-of-time particle jets, which are produced in the 20 to 30% of empty LHC bunch crossings. So we have dedicated triggers in bunch slots greater than 100 nanoseconds away from filled bunches. And this minimizes the background from collisions. So we look at the jet PT in such a data sample. Remaining background comes from cosmic muons on beam halo, beam-induced background, which is estimated largely from the data. Unfortunately, we don't see any excesses. The sensitivity of this type of analysis depends not only on the integrated luminosity, so how many gluinos you might have produced, but also the sample lifetime, how much time you spend looking for their decay. And in this analysis, that was about 579 hours from the 2017 to 18 data set. So we can set limits on gluino masses between 0.6 and 1.4 TeV for various scenarios with lifetimes ranging from 100 nanoseconds to of the order of 1 year. So that concludes my tour through some recent Atlas physics analyses. I just want to briefly look ahead to run 3. So run 3 will go from 2022 to 2024, and we hope for a center of mass energy of at least 13.6 TeV, so a slight increase on run 2, and another 150 to 300 inverse femtobarn of data. This will have high pileup. The pileup will be leveled to about mu = 50 for much of the fill. So this is quite challenging, again, even more challenging detector conditions, and we have various upgrades. So the most prominent of these is the new small wheels in the forward region. So this is a replacement of some of the NCAP neuron stations with micro-mega and STGC detectors. The new small wheel A has recently been completed. This is a photo from a couple of weeks ago in the assembly hall, and actually yesterday it was taken on a truck from the assembly hall to the Atlas surface buildings, and it's now ready to be lowered into the cavern. We also have final granularity of the level 1 electron and photon trigger and a more capable topological trigger at level 1. We also have some improvements on the software side, most notably a new multi-threaded software release, release 22, which will allow us to make more efficient use of modern computing architectures. This plot shows the amount of memory needed as a function of the number of simultaneous worker threads or processes, and you can see the new release 22 is much better in that respect. So we will reprocess all of the run 2 data for eventual combination with this data set. We also have new trigger possibilities, lowering and sharpening the thresholds, and of course new ideas for new physics analyses and searches. So to conclude, I hope I've shown you that Atlas continues to reap a huge physics harvest from the run 2 dataset. We have a detailed characterization of the Higgs boson, including rare decay modes, evidence for rare standard model processes, for example, 4 tops, continuing beyond standard model physics program, and also, which I haven't talked about so much, is an ongoing program of precision measurements exploiting the large and narrow, well understood data set. We have many run 2 results still to come, and of course we also have a strong heavy ion program. We're preparing for run 3 with a slightly increased collision energy, enhanced detector, trigger, and software capabilities. And looking further, we also have the high luminosity LHC to look forward to starting in the late 2020s. And Atlas has a big program of phase 2 upgrades, upgrades of the detector, which have been under development and are now more and more moving into the construction phase. And I just give some of the examples of the different things there. And a complementary program of physics studies, which are preparing to exploit the rich possibilities of the high luminosity LHC and the upgraded detector. So thank you very much for your attention, and I will stop here.
Okay, thank you very much for a very nice talk. Do you have any questions? Okay. I don't see any questions in the box, neither hands raised. Okay. Okay. So if you have no questions, means that it was a very nice talk, very clear, and really impressive, a lot of physics. So Richard, thank you very much for your presentation. And
thank you very much.
Then we'll now move for our last speaker of this morning. Just a second, my windows sometimes disappear. Okay, so next speaker will be Patrick Koppenberg. We'll talk about new physics, new particles and spectroscopy in the LHC era. Brief introduction: Patrick Koppenberg got his PhD from Lausanne University on LHCb in 2002. Then became a JSPS fellowship on Bell experiment at Tsukuba. Then became a CERN fellowship, got a CERN fellowship back to LHCb. It was a lecturer at the Imperial College from 2006 to 2009, and is in CAF since then. It is has been most based on at CERN, where he was LHCb operator coordinator from 2010 to 2014, physics coordinator from 2014-15, LHCb editorial board chair 2018-2020, and now coordinates the development of software analysis for physics upgrade, and also runs some of LHCb social media accounts. Okay, so thank you, and you have the word now.
Thank you very much. Thanks for the introduction. Just checking that you can hear me and that you can see my slides.
Yes, perfect.
Okay, good. So I will speak about hadron spectroscopy at the LHC. I'll first start with a brief introduction of QCD and then a brief detour by beauty baryons before focusing on mostly pentaquarks, tetraquarks. This is mostly from the LHCb collaboration, but there was also input from Atlas and CMS who are joining this this effort. So the reason I'm here is probably because I made this plot that was shown already earlier this morning and was posted on Facebook by UFRG, showing the harvest of new hadrons found at the LHC versus date and mass. And as you will see, the harvest is continuing. I don't need to explain what the LHC is. My apologies to our friends from ALICE. They are not yet in that party, but I'm sure they can also contribute somehow. And also don't need to present the detectors because they were nice introductions to Atlas and LHCb before, and CMS is a bit of the same. So the standard, we all know the standard model that is now pretty solid but doesn't explain everything. I'm going to dig into the areas of the standard model where life becomes difficult, meaning when you have quarks interacting with gluons. And the problem, as you know, is that quarks are bound in hadrons, and they can come as mesons, they can come as baryons, and these were predicted or explained by Gell-Mann, Zweig, and actually also Petermann at the same time. If you want to know a little bit more about the history of that, I recommend this preprint by Petrov. And this happened essentially simultaneously. It's in 1964, which is actually amusing because the Higgs the Higgs explanation also came up in '64 simultaneously by Braut, Englers, and Higgs. So in all these papers, you will find mentions of mesons and baryons, but also of exotic hadrons, which contain 2 quarks, 2 antiquarks, or 4 quarks, 1 antiquark, and of course you can imagine even more exotic stuff. So the reason why they come together is because of confinement, that the QED potential plateaus at 0 at infinity, while the QCD potential raises up to infinity. And this forces quarks to be bound together in hadrons. You will never see a lone quark. It's actually not something that comes straight out of QCD. It's postulated. It works very well, but it's not demonstrated. If you manage to prove that starting from the Lagrangian, then there's a $1 million prize waiting for you. So if you put that together, you can start playing Legos with all the quarks that are available. So if you take the first 4 up to the charm quark, these are the hadrons that you can build in the ground states, and most of them have been found. Not all of them, but most of them. And if you have a look at the masses that were measured and are predicted with present understanding of the theory tools, there's a pretty good agreement. The things become a little bit more complicated once you're looking at excited states. And this is what I'm mostly going to focus on in this presentation. Now let's start with baryons, because baryons provide an interesting ingredient that we will need later for exotic hadrons. These are the baryons that were found at the LHC. There's actually one that is in the ground state, and that's this animal here, the Chi-CC++, a double-charged, double-charmed baryon that is in the meantime very well studied. I will not mention it further in my talk. I will more focus on the other ones. Very recently, that's the last 2 additions to this harvest of hadrons at the LHC came from CMS. And this is a new observation of an excited Xi-B baryon. So the Xi-B is a doublet of a beauty quark and a strange quark and then a light quark. And the the best way of understanding the mass distribution and the spin parities of these hadrons is to assume that the light quarks form a doublet, come in a pair, in a diquark, and then that the B quark is separate, is somewhat separate. So you describe then by determining the spin of the two light quarks and then the total spin of the system, and that works reasonably well. And that's and the fact that there are these diquarks forming inside hadrons is then useful to understand also more exotic hadrons. So this is what CMS has seen. Nice clean peaks of the Xi B minus decaying and fully reconstructed, but they also used some partially reconstructed decay. So they have it at the same time in two decay modes, and they're consistent with being the 3½ minus state. So in a similar vein, LHCb has been looking at omega C and omega B baryons. So 5 years ago, we had this wow experience of opening a mass plot of a singly charmed baryon combined with a kaon in order to find a state that contains a charm and 2 s quarks. And we've seen 5 very narrow peaks. That was a bit of a surprise. And there's also something that could be a wider peak, but we're not completely sure. The problem when you're doing this in prompt production and PP collisions is that you see the peak, you can measure their masses and their widths, but you have no idea what their spin is. And so recently, this is hot off the press. It's actually not yet on press. It's preliminary. It's going to be on archive in the next days. We have studied these same particles, but this time in decays of B baryons. And here we see we have the full access to the angular distributions because we know the initial state of the system that is being produced in this decay of the omega B baryon. So we can study the angular distributions. Now you see that from the data, there's not enough data in order to disentangle clearly these various angular distributions that you would expect depending on the spin that these particles have. So the only thing we can do too far is to exclude some quantum number assignments, and where to place these 5 states on this diagram of quantum number versus mass is still a bit uncertain, but at least we have some information. And of course, with more data, we will be able to understand better how these things behave. And this is then useful information to know which spin parity assignment correspond to which masses, and that allows to refine models that describe baryons, but then also other types of excited hadrons. And if you ask me whether we've looked in B baryons, yes, we have. We also have the same states in the B baryons. Now there are only 4 that popped up in the data. The 5th is probably still hiding, but it certainly exists as well. So that was the small detour from baryons, from which you should take with you the word diquark, because that will reappear later. And let's go to pentaquarks. So pentaquarks and tetraquarks are, most of them are actually a flavor of charmonia. So if you look at the spin parity versus mass diagram of charmonia, you have all these states in black that are observed and are conventional, so expected. And then you have the red ones, which are actually not expected. Nobody predicted those, but they were found by various experiments over the last 2 decades. And this is for the neutral states. Then you have the similar diagram for the charged states. And of course, for the charged states, they are necessarily all exotic. You can't have a charm, anti-charm pair that produces a charged state. So there must be tetraquarks or pentaquarks. And so let's have a look at a few of them. The first that was observed in the first pentaquarks that was observed by LHCb, that was in 2015. We had seen it already a few years before. Actually, my summer student from 2012 was one of the first to actually see that there was something fishy in the mass distribution of a J-psi and a proton in one of the control channel he was using. And so we decided to have a full angular analysis of this decay mode in 6 dimension. And what we determined is that the best way to describe the data was to add 2 more states that were manifestly exotic because they decay to a J psi and a proton. And that sits, there's a narrow one that sits at 4.5 GeV roughly, and the other at 4.4, a little bit below. So we also have evidence of seeing them in the Cabibbo suppressed partner lambda B to J psi proton pion, the state that was the decay that was observed by my summer student. So this is all very good. And then if we start to investigate how the amplitude of these particles of these states behaves, it very much looks like a resonance. So you know that resonances are usually described by a Breit-Wigner distribution that has this shape in mass. Then you have a phase that that increases at the pole and then plateaus. And then if you look at the real versus imaginary part of the amplitude, you make a circle in the complex plane. Now this is exactly what we see with the narrow state. The wider is a little bit ugly in its argon diagram, but it's also consistent with the prediction. So this looks very much like being a resonance. Then we had a look at this again with the full data set of using now run 1 and run 2 data with a better selection. And so we have 10 times more data. And now you can really see them by eye. If you look at the Dalitz plots that was already described by Ignacio a couple of hours earlier, then you see these horizontal bands that correspond to excesses in the J psi proton mass distribution. There's one here, there's another one there. And the other one is actually a new one. So when we look at that in the J psi proton mass distribution, we see that now the peak that we had before is split in 2. So the 4450 is gone and is split into 2 different states, and we have a new state at 4312. We have no sensitivity to the 4380 because this is not a full amplitude analysis. This is just looking at the mass distribution weighted by the angular distribution in the decay. So we're working on the full amplitude analysis. This will come hopefully soon. What is striking is that these 2, the most narrow states, they sit exactly at the threshold of a sigma C baryon and a D meson. And so you may wonder whether these objects are actually compact objects of quarks, or whether they look more like molecules of a baryon and the meson rotating around each other. I must say that here Atlas has also looked at this this decay. They have a difficulty in the sense that they don't have particle identification, so it's hard for them to disentangle the lambda B to proton kaon from the backgrounds from B to J psi k pi, J psi k k, and so on, all the modes that you could imagine. And so it's a heroic effort of trying to isolate this green region and then do an amplitude analysis of the data in it. But they have done that. And what they are getting in their fit is that their fit is much better if they put in pentaquarks than if not. Now, much better means p-values of the order of 50% compared to p-values of 1%. So it's not that they can claim evidence of anything, but at least the fit is much better behaved, which is encouraging. So they should continue that work using the 13TV data, and I hope that CMS will join as well. Actually, a new result in that area is that we've looked at the decay of a BS to a J psi and 2 protons, well, proton and antiproton, which obviously are also sensitive to potential pentaquarks. And we see some structure here at 4.3 GeV, so in the ballpark of the masses you're expecting, but its parameters are not exactly consistent with those of the other states that we've seen in lambda B to J psi proton kaon. So the better understanding of this mode will need some work. So this opens the question of what is a pentaquark. Now it can be a compact object. It can be a molecule of 2 hadrons that are colorless. It can be some sort of hybrid where you have a diquark and so diquarks and heavy quarks rotating around each other. You can have situations with a quark union with a hard core that could be colored or that could be colorless. So plenty of possibilities, plenty of papers that all cite our first PC paper with interpretation. But there's also the possibility that these things are not particles at all, that they are just enhancement caused by triangle singularities, by dynamical effects in the decay. So you could imagine that a lambda B could emit a kaon and then to have a proton in the chi-C meson, so a CC bar resonance that then rescatters into a proton in the J psi. And if things are at the right mass and you have the right energy, you can have sharp peaks arising in the mass distributions, and you can even have Argon diagrams that look like resonances. They're not circles, but the data cannot tell them from circles. So we don't really know with the present amount of data we have what we are actually seeing here. The situation is a bit similar for tetraquarks. Recently, we have observed plenty of new tetraquarks in this decay B plus to J psi phi and the K plus. You see here, this is the Dalitz plot, where if I projected on J psi phi, you see these 4 big peaks indicating the presence of resonances decaying to J psi phi. And in the phi K, the mass distribution, there's not much more, but there's another dimension. So if I rotate that diagram in order to show you the other dimension, then I have the J psi K distribution here, and you see an enhancement as well here that you can very well see by eye on the Dalitz plot. So one of the interesting states that were found here is this ZCS that is peculiar because it contains at the same time 2 charm quark, well, charm anti-charm, and a strange quark. So it's a strange particle, and that's the first case of a tetraquark that actually has open strangeness. Now, we were not first to see it because BESS3 came a few months earlier with an observation of such a state decaying to ds star, and with a mass that is consistent with ours, but a width that is much, much more narrow. So whether it's the same state or not is open. So in my diagram in my counting of hadrons at the LHC, I count this as an observation because it's inconsistent with the state seen by BESS, but we still clearly need a better understanding of what this actually is. So if you ask theorists, so for instance, Mayani and Poloza will tell you, well, these are just the same different partners in a SU3 multiplet. There are theorists who will tell you that these are all threshold effects, and since the kinematics are different, you're getting different parameters, or that there are virtual states that are caused by the same underlying physics, but then depending on what kind of decay you're observing, you're getting different different widths of your enhancement. So that's what I have for exotic at the LHC. There's 2 I didn't mention, but that's because Ignacio mentioned them at length 2 hours ago. So you can go back to this if you want to know more about these 2 states down here and the one up there. And now I have a few slides on the X3872. I'll keep calling it X3872, although the PDG has relabeled it Chi-C1 because now we know it's quantum numbers. It was observed 20 years ago by Bell at the time when I was in the Bell collaboration. It's this little enhancement in the B to J psi 2 pions and kaon decay. So in J psi pi that just sits next to the psi 2s peak that is very prominent. So when I first saw that, I thought, that this must be some sort of charmonium that was poorly predicted. And I was much more interested by the Moon-Mars conjunction that happened on the same day we submitted the preprint. Now that was a big mistake because this stayed. And in the meantime, there are plenty of analysis that studied this state because it's the only tetraquark that we really see in plenty of different production mechanisms and in different decay modes. So it's a very nice object. It's easy to produce, and it's a very nice object to study. So for instance, we studied its quantum numbers, and now unambiguously assign 1++ to this state, which rules out a few hypotheses of it being a charmonium with just poorly predicted mass. And then we recently studied its behavior. Did a very detailed study of its mass shape. So first looking at the Bright-Wigner distribution. So I already introduced that. Now here you also have the amplitude, where you need to see that this is something that happens on the complex plane. So we can actually determine the complex amplitude by just looking at the mass and the width. And so we first need to measure that. The width we determine is about 1 MeV, and this is the first time that any experiment measures a significant width. So far, all previous experiments always had a width that was consistent with resolution. And the big question, the million-dollar question with this state is whether it is heavier or lighter than the D*D threshold, because all mass measurements so far make it sit exactly at that threshold. And unfortunately, we cannot tell, because although we have an extremely good measurement of the mass, it is now as good as the mass of the D* plus the mass of the D bar from the PDG, but they're still consistent within 10 keV. So this is really starting to become precision physics to understand what this state is. So, but Bright-Wigner is really only working if you have a resonance that decays to much lighter objects, which is not the case here, because this meson can actually decay to D*. So you need a better description, and the Flatte parameterization is usually used in that case. So using this parameterization, we determine a mass that is consistent with the one from the Bright-Wigner, but a much more narrow width. And this may seem strange at first, but it's just a different parameterization. And then if you convolve it with the resolution, these two parameterization are actually indistinguishable with the data we have. We would need much more data and a better mass resolution in order to do a better job here, which will certainly which should certainly be done in the future. And then, as I promised, we can then look at the complex plane, and since we measured the mass and the width, we can determine whether this is a bound state, a virtual state, or a resonance, where resonance would be a pole that is sitting off the real axis, while bound state and virtual state, they stay on the real axis. And this is what we get. We actually get two solutions. One of them is it's the best fit, is sitting here. So here you have the mass on the horizontal axis. On the vertical axis, that's half of the decay width. And then what we can do using this Flatte expression is to switch off the couplings to the various channels that we're not interested in, and to see how this resonance would move on the complex plane. So this is a bit science fiction physics, but doing that, we get to this point here, which is just below the threshold actually of D*. So with the data we have, it looks like this resonance is a D*D bound state, but we can't really yet exclude completely other possibilities. Now, you say, okay, problem solved, it's a bound state. But if you look at the way this particle is produced, for instance, the production cross-section versus multiplicity at the LHC for prompt production, then you see that these red points, they behave exactly like what is predicted for a compact tetraquark, and not at all for various models for molecules. So if you asked me, I would bet on a quantum superposition of a charmonium state and a molecule, but definitely we need more information in order to figure out what this is. But it brings me to an outlook, which is actually only this slide. We are now building the upgrade of the LHCb detector. This is the new scintillating fiber tracker that is being put into the pit to be installed on the LHCb detector, which our luminosity is going to increase by a factor 5 in run 3. So we'll have many more possibilities of finding new hadrons, and therefore I expect many more peaks to appear on this collection of peaks that was already shown by Ignacio earlier today. So in conclusion, the LHC is a hadron discovery machine. We are now at 59. I'm expecting more to come very soon. 17 of them are exotic, so we really need to understand how they're made, what they are, and actually the study of baryons, of beauty baryons and charm baryons, can help us understanding how quarks organize in hadrons. And we have one standard candle, which is the Chi-C1, where the DX3872, which we can study in plenty of environments. So this is also a very important particle to study. That's all I wanted to say. Thank you for your attention.
Okay, thank you very much, Patrick. Very nice talk. We have already a hand raised. Please, Michael Albrov, you have the microphone. Hi, Michael. Can you speak? You have a...
Oh yeah, can you hear me now?
Yep.
Yes.
Great. It's very interesting, a tremendous amount of data. About 50 years ago, we did an experiment looking for the K plus P resonance that would have been an exotic. We call it pentaquark now. And presumably you have terrific statistics for that. So can you rule out a pentaquark with in K plus P channel?
That's an interesting one. K plus P in prompt production, we probably would have seen it if it was prominently produced. What would be interesting is to look at it in charm and B decays, actually. So is it still there? Hasn't it been ruled out yet? Because there are plenty of pentaquarks that appeared, some of which were even 4 sigma significant as the zeta plus 20 years ago, and then they were ruled out by a larger statistics experiment.
So this was elastic scattering with a polarized target at the PS, actually, and we did a phase shift analysis, and we had 3 solutions that were ambiguous. One of them had a resonance there, and the other 2 didn't. So it was, it wasn't conclusive. But I can't even remember the mass of that resonance. But I think it might be worth a detailed study.
I'll look it up for sure. Yeah. But that's the energy regime where actually I would expect Elise to have to maybe even be more sensitive. I'm still looking for an opportunity for Elise to join that plot.
Okay. Yes. Thank you.
Okay. Thank you, Michael. Well, we are just in time. So if there are more, I see no more questions. But if there are more questions, just send to Patrick, please. So thank you again, Patrick. And then I hand over the word to Santoro to close the session.
Okay. Thank you. Thank you to all speakers of this morning. And I hope you next time or next LISHEP will be there also presential that time. Okay, thank you very much. Let's go to lunch now here in Rio de Janeiro. And after the afternoon, I invite everybody to come to attend LISHEP. Thank you. This morning is closed.
Thank you, Roberto.